We have been looking into lasers, one of the most important aspects which has been used for quantum computing for a long time. Lasers are one of the ways of our interactions with quantum systems, and laser in itself can act as a quantum system. So, we are looking into the various aspects of the laser in itself, and as we go along, we will also look into its implication in quantum computing. So, we established in the last lecture that population inversion is one of the key aspects of lasing. So, in order to have a laser work, we need population inversion. So, in this lecture, let us look at where we left off. We stated in the last lecture that we needed to have population inversion, in which a state which is a substance has been energized or excited to a specific energy levels. More atoms or molecules are in the higher excited state than in the ground state. The process of producing a population inversion is called pumping. All these processes we have gone through in the last lecture, and the examples which we have been looking at for population inversion are by use of lamps of appropriate intensity or by electric discharge and many other processes. So, in this regard, let us now look back as to how we defined the population inversion. We looked at a simple system of a lower state and an excited state, or in other words the ground and the excited with energies E1 and E2. If we have N1 occupancy in the ground or the lower energy and N2 occupancy in the excited higher energy state, then if it is N1 is greater than N2, which is typically the case for most systems, then radiation is absorbed and spontaneous radiation dominates. That is what we found. On the other hand, if N2 is much greater than N1, then is the condition which we defined as the population inversion, because the other case is the regular case of the population which we generally find. So, in this inverted population condition, if we generate, most atoms or molecules occupy then the excited state. So, there is very weak absorption available, because very few are available in the lower energy state. Stimulated emission prevails and the light gets amplified. So, this is the necessary condition of population inversion which can give rise to the laser. So, we generally looked at it by using the idea of equilibration and the Boltzmann equation of how the occupancy of the states are looked at is given by the ratio of the two occupancies N2 over N1 is given as exponential of the energy difference over Boltzmann constant and temperature. So, that is how the normal system is for Boltzmann under Boltzmann condition or normal conditions, and these are the number of electrons or occupancy of the lower energy versus the higher energy. And for any system, even at let us say 3000 Kelvin, pretty high temperatures, we still see that the relative occupancy of the excited state is very low compared to what it is at the ground state. So, in normal conditions, it is almost always a picture which looks like this. Most occupancy is in the ground state and lesser in the excited state. We also looked at the Einstein's relations, which gave rise to the conditions that we are now talking about. The coefficients that we had defined are the Einstein A and B coefficients, and they can be a little bit qualified in terms of saying that we can label them as B 1 to 2 versus 2 to 1, depending on whether we are looking at absorption or we are looking at stimulated emission. So, For example, in the probability of stimulated absorption, the case when we are having not really stimulated absorption, it's essentially absorption, is when we have the number of lower energy states with a coefficient which is B12 of the Einstein coefficient is going to be equivalent to the rate of the or the probability of this absorption, which can be related by the spectral density, and that is roughly the expression. So, the probability of stimulated and spontaneous emission is more like this particular case, where the stimulated emission is the A coefficient, which is again coming from two state to one state, which is spontaneous, whereas the B is the stimulated case. So, the spontaneous one is the one which is connected, both of them are connected to the excited state. One of them does not need the photon, but the other one does need the photon, and therefore, we can write it in this form. This is another way of writing what we had written in the earlier kinetic model, and both of them are essentially giving rise to the probability of the absorption and stimulated emission, and the Einstein coefficients are the ones which are used here, stimulated and spontaneous emission, as we show here. For a system in thermal equilibrium, the upward and downward transitions must be equal. That is what we used last time, and we can write the spectral density as a form which is of this kind, which is the ratio of the different absorption coefficient of absorptions, as we had seen before, along with the ratio of the number of the two states, occupancy number of the two states, and we can come up with a ratio of that. In the last lecture, we had essentially considered the case where spontaneous emission was negligible. So, our upper term had essentially become equal to 1. However, when we consider that, that also appears in the expression. According to Boltzmann statistics, we have an expression which we have already mentioned, which is of this kind, and that can be related to the energy gap, which is h nu here, and this density that we just defined, the spectral density is essentially equivalent to this form from there to the one which is given as per the Planck's law, because we just used h nu part to come in from the Planck's law part, and so we can use in this form the Planck's law form of the same expression in terms of spectral density. So, by equating these, we can come to a situation where we have a ratio between the spontaneous emission as well as the stimulated emission. So, this is our spontaneous versus the stimulated. The ratio of the two can be found out by using the Planck's law, and this is the expression between the two. So, under the condition that both are equally probable, the absorption and the stimulated emission, which is what is generally the condition for any available photon, we can arrive at this important relation between spontaneous and stimulated emission, and that is with the help of the Planck's law, and we can get this ratio. So, this is another way of looking at it. The probability of spontaneous emission to the probability of stimulated emission, therefore, is once again given by expression. So, what we can find is that no matter what, as we had discussed before, stimulated emission dominates only when h nu over k t is much smaller than 1. So, this is something which is difficult for visible, because for the visible photons or anything in that region, the photon energy is quite high, and the k t is also in this range. So, it is very difficult to get this condition. In the case of microwaves, however, the h nu can be is less than this small number, and therefore it is possible, as you can immediately see, that generating microwave situation is much easier, and therefore maybe you can understand as to why masers were discovered first as compared to the lasers. Anyway, given that that we have arrived at this, the frequency of emission acts to the absorption can be related in terms of the ratio which is given as the n2 over n1 if h nu and this is much less than 1, and that is the reason why as I just mentioned, masers are with the microwaves are a much easier concept in principle with respect to the lasers, where these ratios are very unfavorable in that case, and therefore a two-level laser system in fact was unimaginable, as absorption and stimulated emission process neutralize one another. And so this was the basic idea in the beginning, and Staunch and Shallow went ahead to show that a maser exists by using an ammonia molecule, and they were able to show that they constructed the ammonia, for which ammonia maser with this molecule, and since the principles that we just discussed favors that, it was the first demonstration of its kind of this particular idea of amplification by stimulated emission, and it was possible to do this. Now, for optical regions, this sounded like a very difficult system or difficult process to do it, and so when the idea behind this was being looked at, several important aspects of laser constructions were being looked into: pump source, a gain media or a laser medium, and mirrors forming an optical resonator, where the essential or the key aspects, as you will see now in terms of the laser construction, which is, as you can understand, is going to be a little bit more involved than just a idea demonstration principle which we just started off with, because the idea demonstration principle works quite well and has been shown for the masers at the beginning, but as it can be seen that naturally, at least for a two-level system, as we discussed, it's one of the things which is extremely difficult to achieve in the wavelength regions and the temperatures that we are talking about. So here is actually just a picture of how a typical laser of even this is a laser which is in operation today, for example, a neodymium YAG solid state laser, and in this case a flash lamp pump source is pumping the amplified system, which is amplifying media, which is the laser media, which is then put inside an optical resonator, and a glimpse of this kind of a laser had been already presented in the earlier lecture, essentially showing that we have a almost 100% reflecting mirror on one side, and say somewhere very high but not exactly 100%, just less than 100%, slightly less than 100% reflecting mirror on the other side. So, the little leakage comes out on the output, and most of the gain and all this process continues within the resonating cavity. So, that is the basic idea. The pump source provides the energy to the laser systems. Examples include electrical discharges, flash lamps, arc lamps, and chemical reactions, as we mentioned. The type of the pump source used depends on the gain medium. So, for example, a helium-neon laser uses an electrical discharge in the helium-neon gas mixture. Excimer lasers uses a chemical reaction, and so on and so forth. There are many different kinds. These are both, for example, are in the gas phase, and then there are different ways of looking at it. We just looked at neodymium YAG, which is in the solid phase, and so there are different kinds. So, we can discuss them in many different ways. So, the gain media is the major determining factor of the wavelength of operation of the laser, and it is to be excited by a pump source to produce a population inversion. So, this is the critical part which we will have to think about how we achieve that, where spontaneous and stimulated emission of the photon takes place, for example, and this can be of different kinds: solids, liquids, gases, and semiconductor. Some material part. The resonator is the two parallel mirrors placed around the gain media, the light is reflected by the mirrors back and forth into the medium and is amplified. The design and alignment of the mirrors with respect to the medium is crucial. Spinning mirrors, modulators, filters and absorbers may be added to produce a variety of effects on the laser output. So, these are issues which can be later on looked into in more detail, but roughly speaking, this is the concept that we are talking about, that there is a 100% reflector on one end, just about less than 100% on the other end, and it's been maintained within that, and there is a length within which the whole system is being picked. So, crudely speaking, this is how a laser works. We have the laser being pumped, atoms in the excited state are being generated, spontaneous emission and rare stimulated emission is happening, and that's being put inside, and because stimulated emission is something which is along one direction, is directional. So, what happens is along the direction of the cavity it gets amplified, and initially it is a rare process, but then again that is the one which is dominating, because the spontaneous emission goes in every direction and gets lost, whereas the stimulated one keeps on getting saved. That is what gets amplified, and finally along the laser axis you can start the gain happening, and a steady state laser operation can occur in this matter. So, that is the basic typical idea about how laser occurs. So, a little bit more in terms of the how we are looking at it. So, some ground and some initial to some final state. We have the cavity in which we are having this. We are having the spontaneous emission, which is doing the process of taking the photons in the direction which we need, which leads to feedback in the cavity, keeps on getting into the process, and after several round trips of feedbacks you get the laser beam, which is monochromatic, spatial coherent, temporal coherence and all this. So, if you want actually you can do some number game here. So, you can start with one photon, goes into two, and it just keeps on going in orders of magnitude going higher, and so with like every round trip the number amplifies, and you can see that within a very few round trips so 1, 2, 3, 4, 5, 6 and so on, as you can see it's orders of magnitude, the numbers keep going, and so roughly in 29 or 30 round trips it's some population which is in this case can be like as high as the one country's population, or it could be as high as the world population after a certain number of round trips, and they are all in tandem with each other, which gives rise to the very important aspect of the light amplification. So, that is just the way of looking at it. So, the resonance cavities and longitudinal modes, which are also important in this particular process, needs to be now looked at. I want to remind you that we have come to realize that it is just simple principle of exciting and looking at it is not going to work out. So, we need to look into these other aspects which are very important in the process of laser. It is the design aspect, and that is what we have been going into it. We will also show us what is the best materials and best ideas of choosing the level structures very soon, but let me go over some of these design aspects. So, the other important aspect is the resonance cavity and longitudinal modes which occur. The wavelengths involved with the lasers and masers, for example, spread over small ranges and are also absolutely small. So, most cavities will achieve lengthwise resonance, because that is only in terms of some lambda, and so you can have the cavities set up in terms of how the curvature of the mirrors are, or if one of the curvatures are both are concave. So, basically whether you have a concentric resonator, a confocal resonator, or whether you have hemifocal resonator where one of them is a flat surface, the other one is a curved one, have hemispherical resonator or unstable resonator, depending on the choice of the combination of the mirror combination, we can get these things to happen. And that gives rise to another important aspect, which is the transverse mode of this system, which is you get the lasing having a beam pattern which can be having this important transverse spatial profile, which is due to the boundary conditions and wave equations of these beams being stabilized within the cavity, or how they are forming the different modes within the cavity. And so, we have both transverse as well as the other one was the longitudinal modes, and the transverse modes are the ones which is we are after in terms of the laser is the TEM transverse electromagnetic 00 mode, which is the first one which has the best Gaussian looking mode, and that is given as the intensity which is given by this form. And we are essentially interested to just consider this as our Gaussian intensity profile, and most cases when we talk about a laser, we would be essentially taking the transverse electromagnetic 00 mode, which is the Gaussian mode. And if it has other modes, then we would like to work it out to a point where it becomes an extremely high order mode, which again sort of can be assumed to be a Gaussian mode. That is how we get away by almost always treating a Gaussian mode for the transverse beam. The principle of the population inversion, as we have been discussing for a two level system, is not very exciting. In fact, at thermal equilibrium, we know that we have this problem that we have to get the inverted system, and that is what we found, that for a simple two level system it is a very difficult task to do at room temperatures for achieving a lasing system, because as we know, for a maser it is possible, but to get that for a lasing system for a laser. So, for the laser action to occur, N2 must be greater than N1. That is what we have looked at, which is the population inversion conditions, which is not quite possible for two level system in thermal equilibrium at room temperatures for two level system that we have discussed. In fact, if we look at it carefully, what we find is that to achieve the population inversion for a two level system, it implies a negative temperature, as we show here, because of these population inversions were incorrectly referred to as negative temperatures, and that was the reason why lasers were considered to be something which will not be possible when Meinman initially approached the problem. So, this was one of the reasons why lasers were thought of an impossible scenario even after the masers were discovered. So, the question which Meinman looked at was to ask that if negative temperature is not possible, how can a population inversion be created and maintained, and he looked into this idea of pumping, which is the principle of continuous process of providing energy. It could be in terms of optical, where it can be flash lamps and high energy light sources, could be electrical application of a potential difference across the laser medium, or as we know in present day semiconductors, where we have movement of electrons in junctions between holes. So, over the years this has become the process of pumping has become more and more refined, but generally this was the initial principle behind it. And one of the things which Meinman finally was able to achieve was to use a medium which was just not simple 2 level, but a 3 level, and now this class of lasers can also be defined in terms of the level structure that we use. One is the principle of 3 level lasers, where we have states which are more than 2. So, we have the excitation which goes to a highly excited state, from which it has a fast transition to some metastable state, from where the laser transition occurs. Now, this is a possible scenario because the metastable state can be something where the population can come down after going through the highly excited level, and so it can grow the population of the metastable state if it has stability to some level, so that it does not decay quickly, would mean that it will accumulate population, and a inversion of population with respect to the other state being looked into where it started from can get higher, and so you can have an inversion. So, this is by using or involving more than 2 states, this can be looked at, You can also have a 4-level system, for example, where the highly excited state comes to another as before the metastable state, and then there can be another lower laser level, which is not exactly the state from where you started the whole process. And this is a in some sense is a much easier way of producing an inversion process, because the lower level state, which was with respect to which the metastable state is being populated, can easily achieve the inversion process, because it could be a situation where neither of them had enough population to start with, and so bringing in the population through the highly excited state to the metastable state can quickly achieve the principle of population inversion. So, by going to higher number of states involved, you can actually get the principle of inversion happen, population inversion happen, even without the concept of negative temperatures, and that is one of the things which led to the important aspect of the laser. So, in some sense the laser system can be once again be looked at as the active media which is being excited or being pumped by the excitation mechanism, and which is being put inside a resonator, one of the side to have the feedback mechanism, the part from which some part of the energy is being taken out technically is known as the output coupler, and the other side from which almost no light or the no energy leakage should happen is known as the high reflector. So, this is basically the principle. The energy pump source creates the population inversion in the gain media, and the two mirrors that form that are being referred to here are the resonator cavity. So, this is the principle that we use here, in which we more have the idea of a positive feedback, where the amplifier is being fed back into it, and it's cartoon wise, it's like here is the picture where we have the microphone facing the speaker, and then it will be a lot of difficulty in this process, where we know that you hear a high screech because the microphone is feeding into the system, and you have lot more amplification that you need. Whereas if they are looking at two different directions, then there is no feedback or negative feedback. So, you do not see that. In our particular case of a laser, generally it is a positive feedback mechanism because of the resonator which is being utilized for getting higher amplification. So, the active media in these cases can be a simple atom or a molecule. In the case of an atom, it is basically the electrons with respect to the nuclei, which are residing in different electronic levels, which are the population states, and we are using the different states that we just mentioned, and we have to use more than two states, as we know now, and we have to somehow generate a case where the excited state is going to be higher than the other state. So, it could be a 3-level system or a 4-level system, depending on how we are achieving that. In case of thermodynamic equilibrium, which we had seen before, it was the case where we knew that we have to use the Boltzmann distribution and so on and so forth, and we had found out that it was not possible to do things with just simple two states which are right next to each other, the ground and excited states. And but we can go back and look at this same principle, what happens when you go to the 3-level system. So, generally speaking, there these are all single photon interactions between the radiation and matter which we are looking at, and there are 3 kinds that we have, as we discussed before. One is the absorption process, where the incoming photon of appropriate energy gap between the two takes the electron to the excited state for an atom. So, for a specific case of an atom, we are now showing here. So, we have this rate which can be related to the number of incoming photons with respect to the number of states of the kind that we are looking at. So, N1 atoms being interacting which are in the ground state with the number of photons coming in per unit volume. So, then it can have two different conditions, because the now we have created an initial condition where my electron is in the excited state. So, it could be spontaneous process where it just comes out, outgoing frequency is equivalent to the ingoing, because the energy gap is the same. However, it does not have any directionality. So, as per the solution, we know that we will have that many number of outgoing photons with respect to the incoming, and they are emitted randomly and in all directions. This is the spontaneous decay rate. So, these are the rates equations that we had already looked at, but in a little bit more quantitative manner. So, similarly here for the stimulated process, we have these number of photons interacting with the number of states, number of excited systems, and we can have the output as shown. This is proportionally constant for stimulated emission and stimulated absorption are identical. Basically, we call this, so the stimulated is in the bracket because we are providing the photon. So, we are in some sense stimulating the process of absorption versus the process of emission, and so this is how we have the word stimulated in both, and that is why I had started off with that, but it is all absorptions are in some sense stimulated, whereas emission can either be stimulated or spontaneous, as we are saying here. So, the stimulated photons have the same energy, same frequency and direction, and stimulated emission is a result of a resonance response of the atom to a forcing signal. So, that is the two different cases that we have here. So, in terms of the rate equation, we have essentially written it down in terms of how we had written earlier, and we achieved the same study that we have shown before. Now, the point is, why is inversion possible in a 3-level system? So, say we pump the state 3, which rapidly decays to level 2. So, in terms of these expressions now, we are going to look at the same idea that we talked about physically, and so we go through the same kind of expressions that we had looked at before. And what we can see is that given that we have a total number n for the molecule or the atom that we are looking at, we have these different levels decaying, and if level 3 decays fast and it essentially goes away because you do not see it to appear in the total number at the end of the day, then you have a situation where you can write the difference of the populations in these terms, and so we can substitute them and we can come up with an expression which has the rate of the change of the number of systems of one kind with the other in this kind of a differential equation with respect to time, and we can come up to the same condition with under the steady state condition to this equation, where we will find that we generate the same kind of the saturation intensity that we discussed in the last lecture, which is a ratio between the two coefficients, and we will find that we get to a situation that if our intensity is greater than the saturation intensity, you can get the delta n to be negative, which is exactly what we were looking for, which is your population inversion, and that is the reason why for a 3-level system we can generate population inversion. In fact, as I mentioned before, population inversion is actually easier in a 4-level system, and so this is the similar condition, except that they are now looking at a 4-level system, which where we have a fast decay and a fast decay for the two states that we are going to consider for the lasing action, and this process of going up to another excited state and then the ground state availability is different. And as before, we can write these expressions with the same kind of idea that none of these states have enough to start with, population to start with. So, we can write down these expressions in this form, and we can write n0 now in terms of the population at the ground state, and we can write the total expression again in this form with the same spirit that we have been discussing. And now we have generally considered that our transient in between state to have almost no initial population. So we can get these kinds of expressions written, and we will be getting the steady state expression as before, and going ahead with the same kind of arguments. We find that we'll have this principle where delta n is going to be of this kind, and in this case now you find that this is always negative. So in some sense the 4-level system is a very conducive condition for producing lasing, because in this case, just like the simple 2-level system where it was almost impossible to produce inversion, it's just the opposite where we are almost always producing inversion. So that's the important part here, and the saturation intensity is something which, as I mentioned a couple of times before, is the ratio between the excited state and the ground state in some sense. So we can look at the relaxation rates and we can come up with how these can be quantified, and what we will find is that the B is the absorption cross section sigma, which is because see, the A is appearing because of the time of the relaxation of the state that is being generated. So as long as it's a time scale which is not going to be extremely short, this will be something which will make some sense. So both the sigma and tau depend on the molecule, the frequency, and the various states involved depending on how we define it. And so for here are some typical numbers. So for visible and near IR, we have the h nu as this value, and tau is roughly a picosecond to some tens of nanoseconds for molecules, and and the cross section on resonance for molecules are quite high, are in the order of 10 to the power minus 20 to minus 16 square centimeters, which gives rise to the values of the saturation to be in the range of 10 to the power 5 to the 10 to the power 13 watts per square centimeter, and that's a number density, the saturation intensity, which plays a key role in the laser theory. You need to provide at least this amount of intensity to start off the principle of lasing. So for a laser which is under the very conducive condition, which is a 4-level system, you still have quite a bit of saturation intensity, which is in the range of 10 to the power 5 to about 10 to the power 13 watts per square centimeter. If you look for a similar number for a 3-level system, this number turns out to be much larger, but still it is doable. So here is a comparison now of the 3 different systems that we have now talked about, 2, 3 and 4-level system, and as we have mentioned over and over again, there is no lasing for the 2-level system under the conditions that we have looked at least under normal conditions it is not possible. However, for a 2-level system, if you hit it hard, you can get it lasing. The as I just mentioned, your eye saturation becomes quite high in this case by using similar numbers that we used for the 4-level system, where the lasing is essentially easy because the number density is always in your favor. In this particular case, your inversion is sort of very easy to generate in this case, and therefore it is an easy case, and yet you have to achieve saturation intensity which is roughly for wavelengths in the visible and infrared in the range of about 10 to the power 5 or so, and so which is not difficult at all. This is a very nice number, and you need higher. So that is why if you actually can get to a point where you hit it hard, you can get lasing for 3-level, but in case of 2-level, as we know, it is not possible to get it under these situations. So generally we now are we have sort of understood the way of looking at it. So roughly we are looking for more than 50% of all the atoms to be possible to be in the state 2, that is roughly is how to look at in a 3-level system mode, and these are different representations of looking at the same condition. We call that metastable versus the ground state most of the time, but it depends on which molecule exactly what you look at. But the most important thing is the short-lived high energy state that we are looking at. The reason why I went through the different pictures is also to make you realize that the first laser that was essentially shown by Meinman is the Ruby laser, which was a 3-level system. So it had fast transitions from the excited states on the Ruby atom. That it came down from the higher excited state down to the upper lasing state, and then the laser essentially was possible to get it from the lower lasing state. So laser light was due to the transition of E2 to the 4A2 state. So it was so once this idea was there, it was the basic concept of creating a laser cavity which consists of lasing medium and 2 highly refractive medium, as we have said, and providing enough pump power to get the laser happen. And so here is the first laser. This slide essentially tries to put together all the basic principles that went behind the demonstration of the first laser. It's an important, an extremely important step which I should mention, because when the first laser, the first maser was demonstrated, it was sort of also proved almost equivocal, almost immediately at that point, as we have also shown over and over again, that a 2-level system would actually not be able to produce the concept of lasing at all. The population inversion concept is not going to happen there. And so it was almost like Dr. Meinman was working against all the odds in believing that a laser can actually work. And so it took him a lot of huge challenge at that time, where it was essentially believed that a principle of an optical laser would not be possible. And so it took him a lot of effort to go through the process of providing the principle that it can happen, and he was able to use the idea of amplification with the resonator, which gave rise to the lasing output at 694.3 nanometers. So this is the basic principle. He used electrical pumping by using the electrode to pump the laser system from the lasing medium, which is the Ruby in this particular case, and that's how he got it. The energy input was laterally provided, which was the amplified medium, and this is what the chromium ions, those were the ones which were necessary in the Ruby crystal, which gave rise to the lasing medium. So 4-level system would have been much easier, as we know, and as long as we use a 4-level system, it will be much easier to get an amplification system happening. And so a lot of work has then gone into the 4-level system, which gives rise to lasers which require much lower pumping. And one of the first lasers in this category is the helium-neon laser, where the helium and neon are put together inside the system, inside a gas cell, and the helium is excited, which then transfers the energy by collisions to the neon, which has those exact metastable energy states wherefrom the lasing can occur, and to its higher excited state, which is not the ground state, and therefore lasing is much easier because it becomes a 4-level system. So this was the first demonstration of the 4-level system in some sense. The laser threshold issues can be looked at by calculating the losses, because as you go further into this idea of lasing, you have to also take care of the principles of the thresholds, and in this case the sources of losses can be scattering and absorption losses by the mirrors, output radiation through output coupler, scattering and absorption losses of the active medium and the sidewalls, diffraction losses because of the finite size of the laser components, and at threshold the gain should be equal or higher than the losses, and that is why the threshold is important because unless you are able to at least match the gain to the losses, you would not be able to see a lasing action. There are some certain other very important issues also, that the gain spectrum can become very broad because of this the line shapes that we are looking at now are due to many photons coming out which are being amplified, and the fluorescence line shapes can get broader due to the Doppler broadening and other processes which can happen because of multiple photons coming out at the same time, and that has its advantage as well as disadvantages. The bright line spectra of helium and neon is sort of being shown here, which are at various different wavelengths, but lasing generally occurs at 633 nanometers, 632.8 nanometers as one of the popular wavelengths of the neon, of the helium neon laser, where the transfer has occurred. The broadening of the gain spectrum is due to the as I mentioned, due to the Doppler broadening and collisions with respect to the natural line width that we are considering. So, for instance, for the helium neon case, which is atomic line transitions which are extremely narrow due to natural line width, the laser line width of the would be larger due to the broadening and collisions. At this point, I'd like to just quickly go through some of the classification types of the active medium which are done by in terms of the active medium for these lasers. So, we have already looked at some of them. One of them is the gas lasers, which are atoms, ions and molecules of all kinds. Solid state lasers, we have already looked at a ruby laser, for instance, and there are semiconductor lasers which are diode lasers, unipolar quantum cascade lasers and things which are more used recently. One of the other popular lasers which have been around for a while is the liquid lasers or the dye lasers, where a dye molecule is being used as a very nice absorber and having a wide absorption region where you can actually tune the wavelengths to the certain energies that you need. And there are X-ray lasers and free electron lasers and many other different kinds of lasers. So, we already know of the chromium active ion, which is essential for the ruby laser, for instance. The host is the alumina, which is the reason of the ruby crystal. It acts as a host, whereas the chromium is the active medium which leads to the lasing for the system. So, it is the 3-level system as we mentioned before also, but this is the level structure, and this is how the solid state laser, as we shown before, was shown to work. Operation wavelength in the is at 694.3 nanometers. It's actually still red. It's very near to infrared start, around 700, but it's still quite bright red. It's a 3-level system, absorbs green, blue radiation to give rise to this. Gain medium is the crystal of aluminum oxide with small parts of atoms of aluminum, which is replaced by the chromium 3+ ions. So, that is the active source that we are looking at. The pump source is a flash lamp in this case, and the ends of the ruby rod serve as laser mirrors. It was the basic idea behind this. Again, for the gas lasers, for example, the laser active medium is the gas at low pressures, roughly a few millitorrs. The main reason for using the low pressures are to enable electric discharge. So, most of the gas lasers are based on electric discharge principles, with a long path where the electrodes are at both ends of the long tube to obtain narrow spectral width, not expanded by collisions between the atoms. That is another important way to reduce the line broadening. The first gas laser was again operated and shown by Meinman in 1961, 1 year after the first ruby laser was demonstrated. And the first gas laser was a helium-neon operating at the near infrared at 1152.27 nanometers. The gas laser, typically the ones that we use nowadays are in the visible region of 632.8 nanometer. So electric discharge, and the gain media is a ratio of 5:1 mixture of helium and neon gases. The helium is being excited and being passed on to the neon gas. The energy process goes interconversion into the neon gas, which is the one which is our active laser media in this particular case. So, here it goes through the collisions into the neon system, and it goes through the principle where we are able to get the lasing in this particular case. The first lasing, however, was shown at 1152 by Meinman in this particular region, whereas today this is the one which is more typically used, which is 632. So, there are many ways of looking into these kinds of lasers, but we do not want to really spend much time on these anymore. These are glass chambers in which the gas is being stored and all that. Roughly speaking, we have the electrodes and where the gas amplifying mixtures are put, and if you want to look at it, there is a high voltage which is what is creating the discharge, and that is what is being shown here. Amplifying medium, the flash tube is doing that, and we get the laser tube. The other important gas laser is the argon ion, where the pumping is being done by, again, plasma is being created by electric discharge, and then we get different laser transitions. It is again a 3-level system, and so you go to the excited state when you come to the metastable states, and then you see the laser transitions at different wavelengths, 514.5 or 488 nanometers, and which is the higher plasmonic transitions which are being used. So that is why it is an argon ion laser is being used. It can provide high power, but it again has low efficiency because it is a 3-level system. The other important laser system which has been used for a while now is the liquid laser system. It was very popular until about 5-10 years back, but due to many other issues, dye lasers are not that extremely popular nowadays. However, it is important to provide the details on this very important class of lasers, where it is the complex organic dyes such as rhodamine 6G in liquid solution or suspensions which have been utilized. The pump sources can be other lasers or flash lamps, can be used with a wide range of wavelengths. That is the key issue why the dye lasers became very, very important, as they can be having a huge tuning range of the laser depending on the exact dye being used. So, you change the dye and you can get a new laser, and that is the reason why this tunable dye laser sources, as it was one of the biggest source of this. Sorokin was one of the first persons who were involved in this process of this dye lasers, and it has gone through a lot of development, and it is a very useful lasing system because many spectroscopic applications needed tunable lasers, where the dye lasers played a very important role. Typically in this process, there is either a dye cell or a dye jet into which the pump beam is being focused, and that sets off the cavity, where there can be different ways of selecting the wavelength by using a grating or prism, or and then there is this cavity which is inside which the laser is being put, so that you can get the output. And it is a 4-level system, and the energy absorbed in the dye creates a population inversion, moving the electrons into an excited state. So, in this case, this is sort of like the 4-level system that we can see in a dye laser, where you have the efficient pumping to the excited state, and this excited state has very low relaxation to the place where it came from, the ground state. Instead, it quickly goes into a metastable state, which is sort of stable because its relaxation into the other possible state down there is low. creating a population inversion with respect to another metastable state, which can again undergo a fast relaxation when it is going there. So, that is why this is a very important 4-level system which is being used, and in case of the dye, this is a big molecule where they have complex energy structures, and the transitions are going from different ground to excited levels, and the vibrational states of these different levels can be utilized to get the transitions. And you can look this one up. There are many different kinds of the dyes which we can use, and so on and so forth. It's technically a 4-level system, as we have been saying, and the time scales involved are important because that can give rise to different kinds of things. One other important 4-level system which I mentioned, I showed this laser, so I thought I will just mention it before closing the lecture today, is a neodymium YAG laser, which is again a solid state laser. It's the YAG crystal in which yttrium aluminum garnet, that is the crystal in which the neodymium ion is being used as the. So, our active medium in this case is neodymium 3 plus, which has been shown, and that is the one which is getting pumped into the excited states, which then goes into the upper lasing state, which is one of the semi metastable state, and then there is a lower state available, and so it is a 4-level system where you can get efficient lasing at 1064 nanometers, which is the primary lasing wavelength of this, and turns out to be a very effective and useful lasing, and it is the transition which we look at. So, this is the population inversion we are looking at between for all these systems, which is very effective. And finally, I would not mention much about it, but semiconductor laser is a laser which semiconductor serves as a photon source, and typically these are direct band gap semiconductors which can be used as small highly efficient photon sources, as also the fiber lasers where you have erbium doping which can create lasing and other kinds of things. We will not do too much about it now because we will have to move on to other aspects. So, most of the lasers that we have talked about have multi-mode laser output, and where there are mode separations, central wavelength, and the typical Gaussian output is there, but then there are these longitudinal modes, and this is a typical laser output, and all the this is the energy diagram again. We have already gone through this. There is another small quick example of the free electron laser here, which also has a very high tunability, but it requires a lot more energy to start with the system, but this works with the principle of electron beam, and output laser beam is visible, or it has a wide range of spectrum that you can get into the infrareds and many other wavelength regions, and here the electron beams are being oscillated and amplified, and as a result of that the light the associated electromagnetic radiation gets amplified, and so you get the lasing output. In fact, lasers exist in nature also. So, here is an example of a gas laser in nature. In the stellar atmospheres of the planetary atmospheres and interstitial mirrors, there are active regions where there are gas lasers which can exist, which are known to exist in nature. And so, with this I would like to actually close this lecture, because in the upcoming lecture we would be looking at the pulsed laser. I just alluded to the idea that we will be having various modes. So, we want to put them together, and then we will have a timed spectra. So, in the next lecture we will be looking at pulse lecture. With this I would like to close. Thank you.